So then once you form your halohydrin, then you just need to treat that with sodium hydroxide in order to make your epoxide. And then again, just in terms of rationalizing this, remember this is an sp3 hybrid carbon, okay? So here we have this back lobe of the carbon to halogen bonding orbital. So that when your hydroxide attacks here, this is in the right orientation for that reaction to occur.
Can you just explain? It looks like to me that then the oxygen ends up on like below the methyl group, but then on the epoxide comes above
Yeah,
it.
but this wasn't a real stereochemical drawing, so so you know the product that we'd get, I would just flip this over and it would be the same thing. All right. So the idea is that for the halohydrin, the OH and the Br always end up anti, right? In this case, if we start off with this flat alkene, we could get these two possible stereoisomers as products. What's the relationship between these two? Enantiomers, diastereomers, what?
They're definitely enantiomers.
You should feel confident in saying that they're enantiomers. If you're not feeling confident about that, you know, you could actually break out your little model kits if you have them and try to visualize that. So in this case, since the oxygen is on top, it would attack here to kick the bromine out. So in this case, we would make the epoxide point outwards like that. And in this case, with the OH at the back, the oxygen would kick the bromine out from the back. So the epoxide that you make look like that. And just to make this make any kind of difference, I'm going to stick a little decorator thing on here. So now when I've done that, what's the relationship between the two of these? Alex? Yeah, no, because I put this here, they're no longer enantiomers, they're diastereomers, right? So we make two different stereoisomer epoxide products. But they're not mirror images of each other. You read?
It's supposed to be a doctor for the college.
Yes. Oh, yeah. So the thing is that, unlike regular ethers that have like regular acyclic ethers, open chain ethers, or larger ether rings, epoxides are very, very reactive types of ethers because embedded in their structure is all of this ring stream. Okay? So just like how we learned that cyclopropane rings are strained and therefore, higher in energy per CH2 group than something like cyclohexane. Epoxides are also very strained, and so epoxides end up also being useful reaction intermediates because where it's difficult for other ethers to react with anything but this, really strong acids and so on. Epoxides can undergo a variety of different reactions. Okay? And the first one will remind us a little bit of the reaction to make the halohydride, which would be acid catalyzed. So in the presence of a strong acid, like if we were to take, we can use propylene oxide as our example. But let's draw it with some stereochemistry so that we can keep note of things. So let's say we have treating propylene oxide with sulfuric acid. First thing that would happen, miracle?